Welcome back, chemistry students. Today we're going to be talking about solutions. We're going to be covering day 1 of our Unit 11 notes, and we're going to begin talking about solutions using a scenario that I'm sure we're all familiar with, which is that salt, sodium chloride, dissolves in water. So the important word there is dissolves. So in scientific terms, we can describe salt, or sodium chloride, as soluble in water. When the salt dissolves, the sodium and the chlorine molecules are going to become uniformly or evenly distributed among the water molecules that we have placed that salt into. So the solid salt is no longer going to be visible when we do this. And in this specific scenario, we are going to say that the water is a solvent and that sodium chloride is a solute. So the solute is going into that solvent, and we have now the sodium and chloride ions floating around. Altogether, we call this mixture a solution. Okay? And so what I want you to do right now, real quick, is pause me and define in your own words and fill in the blanks on the image to the right using these terms. Okay, hopefully you were able to fill in these terms with some definitions. I've written down my science definitions right here for y'all. So I have soluble, meaning able to be dissolved. A solution I've defined as a homogeneous mixture of two or more substances. And if we think back to one of our very first units in this class, we need to remember that homogeneous is just a fancy word for something that looks the same or something that looks uniform throughout. So the prefix homo meaning same. A solution is a homogeneous mixture. It looks the same throughout. A solvent, we're going to say, is a substance that is capable of dissolving a solute, and a solute is a substance that dissolves in a solvent. So this is a thing that's being dissolved. And we see solutions all around us in our everyday lives, and so I'm going to give you a couple examples of solutions of gas, solid, and liquids here. So the first example I want to give us is an example of a solution that is a gas. Air is a great example of a gaseous solution. So we have all sorts of things floating around in the air. We have nitrogen, we have oxygen, all just floating around us. Nitrogen is actually the most abundant gas in our atmosphere. An example of a liquid solution would be salt water, is probably one of the more common examples given. That is a mixture of salt and water, and we, just as we did up here, we dissolved some salt in our water and made ourselves a solution. So with this example, I'd like to come back up and label this picture to make sure that you also labeled this picture correctly as well. So up here, we had our salt, which is going to be our solute. We have our water, which is going to be our solvent. And then together, once the solute went into the solvent, when it dissolved or underwent dissolution, we were left with a solution of salt water. Another good example of a solution, a liquid solution, is tap water. The water that comes out of our faucets is not actually pure water. There are trace amounts of chlorine and other minerals in that water, so tap water is a solution. It's all evenly mixed together, which is, just like we said, a defining characteristic of solutions, looking the same throughout. Okay, and finally, I'm going to give you all an example of a solid solution. A good example of a solid solution are metal alloys. So metal alloys are mixtures of metals. So, for example, my Aggie ring, it is not pure gold. It is an alloy of gold. There are other things in there like silver and copper. So that is a mixture of metals right there for you. Okay? So with that vocabulary and those examples under our belt, we're going to go ahead and talk a little bit about electrolytes versus non-electrolytes, because these also have to do with solutions. So the first thing we're going to talk about is electrolyte. This is a substance that dissolves in water to give a solution that conducts electrical current. So this electrolyte is something that will dissolve in water and give us an electrical current. So what's going to happen is when we have this substance dissolve in water, the ions are going to separate out, much like our salt did up here in our solution of salt water. And when those ions separate from each other, they are now free to move about the solution, making it possible for that solution to conduct an electric current. So we can conduct electricity through these solutions. Any soluble ionic compound is an electrolyte. And just as a reminder, in order to check if something is soluble, I'm going to even write it here for y'all. Check if something, or let's actually clarify, check if an ionic compound is soluble in water by looking at your solubility rules. My bad, I kind of had that off to the side. So there we go. So remember those solubility rules, we can find them on our formula chart on our third page right here. You can take a look. Remember, if we have that AQ, aqueous, we are dissolved in water, we are soluble. And if we are a soluble ionic compound, we are an electrolyte. So two examples of soluble ionic compounds. The first is one we already talked about, sodium chloride, our common salt. Another example would be something like potassium bromide. Potassium bromide is also soluble in water. It is an ionic compound. It is made up of ions. So there are two examples of electrolytes. On the other hand, sugar, sucrose, common table sugar, has this chemical formula, C12H22O11. This is an example of a non-electrolyte. So this is a covalent compound. It will dissolve in water. It is polar. So we're going to talk a little bit about how compounds dissolve in water and polarity in a second. But just so you know, sugar will dissolve in water. You've also probably witnessed this as well. But since it is covalent, it is not going to dissociate into ions like sodium chloride and potassium bromide will. So since it is a covalent compound, it does not conduct an electrical current. It does not separate into ions. It is considered a non-electrolyte. Okay. And just so you are reminded what we wrote up here, this is sucrose, which is table sugar. Okay. So we're going to go ahead and flip to our next page. We're going to talk about factors affecting the rate of dissolution. So if we have a solute dissolving in a solvent, we have a solid solute dissolving in our solvent, there are three ways that we can speed up the rate of dissolution, the rate that things dissolve at. So these three ways are to heat it, crush it, or stir it. And you may be familiar with these as well if you like to make iced tea. Okay? So if you heat up, for example, a glass of tea, you increase your temperature, you are going to make it easier for your sugar to go ahead and dissolve in that tea. So increasing the temperature is going to increase the number of collisions between our solvent molecules and our solute molecules. So this is going to, or our solute, like salt, this is going to make a more frequent collisions happen and cause our solute to dissolve faster in our solvent. Okay? So our second way to increase our dissolution is to crush our solute. So if we crush our sugar up, if we have a block of sugar and we crush it up into smaller particles, we're going to create more surface area on those particles, and so this is going to speed up the rate of dissolution. And finally, if we stir something, this is going to help us increase our rate of dissolution as well. So if I'm going to stir in my sugar to my tea, I'm going to help disperse, I'm going to spread out. In other words, that's another way that we can say disperse. We're going to spread out our solute particles, and we're going to increase the contact between our solvent and our solute. So our sugar is going to be in increasing contact with water. Okay? So those are our three ways. Heat it, crush it, stir it. Now we're going to move on and talk about polar versus nonpolar substances. So a very big, important rule when you are talking about solutions and solubility is that like dissolves like. Okay? We are aware from real-world experience, and the image here, if you have not ever done this yourself, that oil and water do not mix. So right here we have, actually I'll label that in a sec. We have some oil mixing in with some water. It is not mixing in evenly. We see these globs of oil spread out in that water. So just a reminder, water is a polar solvent. It is one of the most common polar solvents that we use. For this reason, it is sometimes called the universal solvent. Oil is not polar. Oil is nonpolar. And I just told you that like dissolves like. What that means is that polar solvents will dissolve polar solutes. So let's even write that down. Polar solvents will dissolve polar solutes. Okay? So since we have oil here, nonpolar, and water up here that is polar, these are not like things. They are different. Because they are different, they won't mix. Again, like dissolves like. So we have over here in our image some nonpolar oil refusing to evenly mix with that polar water. So there's some things happening at the atomic level that's preventing those things from mixing. Okay? Right here we're asked, is sodium chloride polar or nonpolar? How do we know? Go ahead and think about that for a second. Pause me, and then come back and see if you got the correct answer. Okay, so there is our answer. Hopefully you got the same thing as me, which is that sodium chloride, salt, is soluble in water. Remember, like dissolves like. Water is polar, so sodium chloride is also polar. Now we're going to talk a little bit about pressure, specifically how pressure is going to impact the solubility of gases in liquid solutions. Okay? So when we have a solid solute, the change in pressure is going to have very little effect on the solubility of those liquids or solids in liquid solvents. Okay? If we have a gas, however, an increase in pressure is going to increase the solubility of a gas in a liquid. We call this Henry's law. Okay? So we can think about this law in terms of sodas, because this is probably the most common area of our lives that we encounter this phenomenon. Okay? So in a soda, you have a gas dissolved in a liquid solution. You have carbon dioxide dissolved in a liquid solution. That's why soda is bubbly. We have all that gas bubbling through it. Okay? Before we open a soda bottle, we have over here in this picture indicated high pressure and a high concentration of gas in that bottle of soda. So the soda is unopened, we have high pressure because that cap is on, and we have a very high concentration of gas in our soda. When we go to open that soda bottle, we are going to decrease the pressure. We open up that soda, we take off that cap. You might hear a little release of air because the pressure is decreasing. And when we do that, we decrease that pressure, we are going to decrease the concentration of gas. So that gas is going to come out of that solution, and we're going to have less bubbles now in our soda. Okay? So knowing that that happens, I want you to try and use Henry's law to explain why a bottle of soda goes flat after we let it sit a few days open on the counter. Okay? I want you to use the word solute, solvent, gas, pressure, and concentration in this explanation. So go ahead and pause me, try and do that, and then come back and check if you were correct. Hopefully you came up with a solution that is similar to the one I wrote down here, which is that when you open a bottle of soda, the pressure is going to decrease. When that pressure decreases, the concentration of gas in the solution will also decrease, as gas, our solute, is leaving the solvent. I'll leave that up there for a second. And then we're going to go ahead and flip to our last page. We're going to talk briefly about how temperature affects the solubility of gases in liquids. So we already learned that increasing the temperature will increase the solubility of solids in liquids. Again, our example that I gave y'all was a sweet tea. Sometimes we make sweet tea at a high temperature in order to increase the amount of sugar that we can go ahead and dissolve in that tea. If you are a fan of iced tea like me, then you're going to go ahead and cool that down again before you drink it. But we do increase that temperature to increase that solubility of our sugar. Okay? It's a little bit different when it comes to gases in liquids. Okay? So similar to our soda example, we had a little bit of a different thing going on. So when we increase our temperature of our solution and we have a gas dissolved in a liquid, an increase in temperature is going to actually cause a decrease in gas solubility in liquids. Okay, so we are asked right here, should you store your open soda in the fridge or on your counter, and why? So again, I want you to take another second to think about that, and then check your work with me. I have now added my explanation in here. I made myself another note. I wrote that high temperature equals low gas solubility because that's what this statement up here was trying to tell us. And then I went ahead and said that you should store your open soda in the fridge because a lower temperature means higher gas solubility. And so if we store our soda in the fridge, our soda will theoretically stay bubbly longer if we do that. So hopefully you were able to get some tips for storing your soda and understand solutions a little bit better with this introduction video. If you have any questions, grab yourself a chemistry teacher, let them know, and we can help you out. Thanks for watching, y'all.